Bismillah ar-Rahman ar-Rahim. Today we're going to start chapter 4, particular solutions. In this lecture, we'll try to simulate more realistic loading, such as impulse, step, linear, exponential. The sinusoidal, I will let you do it, review it from the book. And I know we discussed this in the class, but I would rather spend more time in impulse, step, linear, and exponential, since these are the more realistic loading that you might see in the field. We need you for the next week to start reading chapter 5 or lecture 5 and to submit the classwork for chapter 4. And there is no announcement to mention here. The learning objective of chapter 4, that we want the student to graphically and mathematically represent responses of a CSTR to pulse, concentrate, linear, and exponential loading. And also, the student has to describe CSTR in series or reactions in series. And we'll be giving an example of reaction in series later on. And of course, we want to describe them graphically and also mathematically. Student later on can calculate the critical time. This is a very important time, okay, that we will have to have it for design, and the critical concentration. So critical time, critical concentration, these are extremely important, especially for responses to an exponential loading. Let's recap from the previous lecture and try to see what was the general mass balance equation that we did last lecture. Remember, V dc over dt, volume dc over dt is equal loading minus flow rate concentration, that's out. That, of course, I'm not going to put out, but that's C without anything, it's out, minus K, the rate of decay, the rate of degradation, times volume, times concentration out, minus if there is any settling properties of the particle times the surface area times concentration out. So this is the equation, the general mass balance equation. So if we have like a CSTR, or if we have a bond, or if we have like Kuwait Pay, if we have loading coming in, whether the loading is point, non-point, whatever, minus, of course, the Q. Of course, here there is a Q coming up, and here there is Q leaving. Q in and Q out should be the same. And this is the concentration leaving the bone, which is the concentration inside the bone. And of course, you'll have some settling velocity of the particle, an area of the bond, surface area of the bond, and of course, and the volume of the bond. So all of these should be listed or measured before you do the mass balance general equation. Now, if you want to solve it at steady state, you have to assume dc over dt equal to 0. So this could be equal, the concentration out is equal to the loading over Q plus KV plus settling velocity A. You should know, differentiate between volume and settling velocity. And for our general solution, since the loading at T is equal to 0, then the concentration at any time T is equal concentration initial e to the power minus lambda T. But in reality, W is not equal to 0. This is if the loading is equal to 0. W is not equal to 0. So that's why we will have to go and check what type of loading we have and what type of information we have. But before we do this, let's just solve an example. Exercise 2 weeks. So this is 14 days. After a sewage treatment plant began to discharge 7 million gallons per day, 7 million gallons per day of wastewater into a small detention pond, the concentration of a herbicide, which is like a pesticide, decay of that pesticide is 0.12 per day, and the concentration in the bond. So you have the bond. So the concentration inside the bond, which is the concentration outside the bond. Okay, so this is the concentration outside the bond. If you say concentration in the bond, which means the same concentration outside the bond, is equal to 140 milligram per liter. So this is the concentration in the bond, 140 milligram per liter, and that is concentration effluent. Volume is given 150,000 meter cube. What is the concentration of the herbicides in the treatment plant effluent? Well, there's a spelling error. There's another F here. Okay. Note that 1 meter cube per second is equal to 22.8245 million gallon per day. Let's convert, first of all, 7 million gallon per day. So you have meter cubic per second, million gallon per day, 22.0245, and this is 1 meter cube per second, this with this. So you'll end up with 7 over that, and that's gonna give you 0.31 meter cube per second. And let's convert second to day. Second up, minute. 1 minute is 60 seconds. And then second with second, and then minute, hour. 1 hour is 60 minutes, and then hour, day. So now it's going to be meter cubic per day. So this would be equal to 26,497. 26,497, and that is meter cubic per day. And that is the flow rate from 7 million gallon per day. I converted to meter cube per day. That's 26,497. Okay. So let's try to go to the next page and try to solve it. Now, first of all, we need to find out lambda. What is lambda? Lambda, if you go back to the previous lectures, Q over volume. Sometimes I do volume like this, depending on the way you write volume, plus K. So Q, we just found Q, 26,497, and that is meter cubic per day, divided by 150, that's given in the problem, 150,000 meter cube, plus the K is given 0.12 per day, and that would give you 0.30 per day. Okay, we know that Q over V plus K are extremely important, and we have to account for decay, and we have to account for settling. And since there is no information about the settling properties of this type of organic, so that's why we should not include it. We are only including whatever is available. Now we need to find out concentration, initial. We should find out, first of all, concentration after 14 days. So I'm going to put it at concentration final, which is concentration after 14 days. If you go back and check the equation for this type of general solution, is equal. What is C naught? What was inside the bond initially? There is no information about that, which means that this can be considered 0 plus loading over lambda volume times 1 minus E minus lambda T, and that was given in the note. And since we will assume that initially the bond is clean, there is no pesticide inside the bond initially. Okay, so this is going to be 0, assumption 0, and now we have to convert the W. Remember the loading, it's equal to Qn times Cn. This is the flow rate N. So we'll just do it like this. Flow rate N times concentration N. C naught, it's initially C naught inside the bond is 0. There is no organic initially inside the bond. So we will assume that this is 0. We're not going to include it. Okay? So now we'll try to put the concentration after 14 days is equal Qn Cn over lambda volume 1 minus E minus lambda T, and that would give you C after 14 days, which is 140 milligram. This is 140 milligram per liter. Okay, equal Qn. We have Qn 26,497 meter cubic per day, and Cn is unknown. We need to find out Cn because he wants to find out the concentration of this organic in the influent. Okay, Cn is needed, and this is divided by lambda, which is we found here 0.3 per day, times the volume. Volume is 150,000 meter cube, and this is 1 minus E to the power minus lambda 0.3 times T, and T is 14 days. Okay, so now you can see day with day, meter cubic with meter cube, and day with day. You'll end up with milligram per liter of Cn. If you just plug it in, you will find out that Cn initial concentration coming in with the loading is almost 241 milligram per liter. You should have your unit put with the number, and you should have the digits in 3 significant figures all the time. So this is the way we used to solve it if the loading and the solution was general. Now, let's try to compare it before we proceed to particular solution. That general solution, we are trying here to describe the natural behavior of the system when there is no external input or loading. So loading is equal to 0. Okay? In this way, the general solution represents how the system returned to its equilibrium on its own. There's no forces from outside. The other side, what is particular solution? In particular solution, describe the response of the external loading or disturbance. Of course, this applies when the forcing term W is not equal to 0 this time. W has something. Okay? And this in this type of solution, we are capturing how the system behaves because the added inputs, such as pollution load, such as nutrient addition, such as withdrawals, if there is any withdrawals coming out from the system, all going to be models, okay, and all going to be captured. Sometimes you'll have a combined solution, like if you have like a full system solutions, you could have general solution, you could have particular solution altogether, which allow simulation of perturbations and return to the steady state to the system itself. Here we're going to allow us to simulate how the system responds to a disturbance and how it's eventually returned to its steady state. So why this is very important in environmental system? Of course, the general solution showed the system internal stability, decay, settling, natural removal. And the particular solution also shows how the system reacts to human or environmental changes. Pollution increases, pollution decreases, accidental spills, flow changes, increasing or decreasing. And together, general solution and particular solution can always allow us to predict concentration over time. And that is what's extremely important. Let's start with pulse loading. So pulse loading, it is the meaning of that, it's an instantaneous pulse mass into the system. For example, spill, a truck, let's say a truck in Jabir Bridge has a car accident and the whole truck fell down to the Kuwait Bay. And of course, let's say the truck has some fertilizer. And all these organics fell down in one place. So this is, we could call this a pulse loading. Okay? So it's an instantaneous pulse of mass of organic into the system. Spill, accidental releases. So how could you graph it? Let's see if we have this time. and this is loading. You can see that the loading was 0 until the accident occurred, the spill occurred. And then you will have a pulse increase in the loading, and then later on go back to 0. Loading is 0. Initially loading is 0, and then during the accident, let's say start with this time is equal to 0. Time equal to 0, there's a pulse, and then later on there is nothing. There's no more loading coming in. There is no external loading. If you want to represent this into the concentration, you can do it like that. This is time, and this is concentration. And initially, let's see, this is initially, okay, the concentration was 0, because there was nothing, everything is clean. And just like that, because of the pulse, it will increase the concentration to a certain value. Let's say this is C naught. That's going to be the initial, and this is going to be time equal to 0, time of the accident. And then later on, you will have an exponential decay of the concentration until it reaches 0. And you could call this exponential decay. And this is like, of course, at this place where you have the spill, of course, Kuwait Bay is really huge, and CSTR is also huge, and bones are really, really huge. So the waste will have an instantaneous well mixed at this point. Okay? So that's why it will start from a higher concentration to a lower concentration later on time. Let's find the equation that is related to this pulse loading. dC dt plus lambda c equal mass over volume times delta. So there is something that will represent the pulse, and this is the delta function represent how much of the spill is there, how much the pulse spill is there. So delta T represent the pulse loading. And this mass, this is the mass. Let's say the truck has 100 ton of fertilizer. So this is the mass of the spill. Okay? And then if you solve it, if you solve this equation, you're going to have CT equal mass over volume e to the power minus lambda t, and this mass over volume is equal C naught, initial. So this is going to be the initial concentration of the organic at time is equal to 0. And that's going to be considered like this, CT equals C naught e to the minus lambda t. And of course, from here, this is an initial value T0. This is during the spill or at instantaneously at the spill time. And after that time, this is the time that you will see of the concentration changes after the spill is done. Okay? So this is the first case, the pulse loading. Now, we're going to go later on to the next case. Next loading is step loading, but we'll assume that C naught is equal to 0, which means that there is initially Kuwait Bay is clean. Of course, that's not realistic, but we can assume that it is clean. So there is no initial concentration of that organic chemical in the water system. So if you plot it, it's going to be like this. And the step loading means, I'll show it to you right now. It's time, if you time it, loading, initially it was 0, the loading, and just like that, there's a pipe in Kuwait Bay, you open it, and that pipe brings all these organics. So at initial time, it will increase the loading, and then the pipe is not closed. Let's say that there is a pumping station somewhere in Kuwait, and this pumping station was pumping toward a wastewater treatment plant. And let's assume that this pumping station is not working. So we have to do a bypass, and the bypass has to go to the ocean, so which means that there's a pipe that's going to be disposing wastewater to the ocean. So at time equal to 0, the loading was constant, steady, or step. It might take 1 year. It might take, depending on how much, how faster is the contractor to fix the pumping station. It might take 1, 2, sometimes, especially when the contractor is not in force, it might take 5 years. So this loading is staying for a longer time until they fix the pumping station. So I'm assuming it's a pipe. And this is the loading that's going to be there for a longer time. If you want to do this for concentration, this is the time, and this is the concentration. You can see at time 0, the concentration starts from 0 and goes to a higher value. And this is the new steady state. The new steady state. So this is the new steady state solution for the concentration. And let's just call this C prime. So this is the new steady state concentration at the, like maybe after 2 months, 3 months in the water system. So you can see the loading initially it was 0. So here initially it was 0 at T less than T naught. I'll just call this, you could call it T naught or you could call it T at 0, whatever way of doing it. And for T higher than T naught, loading is equal to W. So this loading is fixed, constant. That's why we call it step loading. So if you want to plot, if you want to do the equation to graph it later on, dc over dc over dt plus lambda c equal W loading over volume. And if you solve it, C at any time t, loading over lambda volume, 1 minus E minus lambda t. So we could notice something here. At t goes to infinity, when time goes to infinity, higher, let's say 1 year, 2 year, 3 year, 4 year, this term would be almost 0. So this is 0 as t goes to infinity. Oh, you could cancel it. So 1 minus 0 is 1. So concentration at t is equal to infinity would give you C prime, okay, which is going to be equal W loading over lambda volume. This concentration C prime, it is the longer term for steady state solution. Okay, this is if C naught is equal to 0. What will happen if there is something initially in the lake, or something initially in the CSTR, or something initially inside Kuwait Bay? Let's look. Okay, so let's just summarize the meaning of WT. It means the external mass loading rate. CT, which is the concentration response in the system, inside the CSTR, inside the bond, inside the Kuwait Bay. And the WT, if you want to visualize it, is shown as a step change, 0 to constant later on, to a higher value of W, but later on it's going to be constant at time is equal to naught. You just saw it here. It is 0 initial and then goes up to higher, and then later on it will be constant throughout. CT, shown as a rising exponential approaching a new steady state. You can see it here. What is it? It is 0, and then it will rise all the way until reach C prime. Okay, the new steady state concentration. Now let's look at step loading when the initial concentration inside this water system is not 0. T versus W, which means when I say that initially it is not 0, which means that there was initial loading. let's see, at time 0, and let's just make it T naught. At time 0, there was an extra load, and then later on you'll have a step loading, but when the initial concentration was not equal to 0. Okay, and we could call this extra loading as delta W. Okay, loading is equal to 0 for T is less than T naught, and then loading is equal to W when W, of course, this is the new one, that's the new W, but it's W naught plus delta W to account for the new W at the end when T is higher than T naught. If you want to plot the concentration versus time, you can see initially the concentration was fixed as C naught. This is time initial. And then later on, since you have an external loading, it will go the concentration to a higher value. Now later on, C prime will be approached that value that we're gonna model right now. So if you want to do the model for this equation, C at any time T is equal C naught, and this is going to be C naught, the initial concentration, plus delta W, and that is this difference in loading from initial to the final over lambda volume, 1 minus E minus lambda T. And the same thing if you are assuming that T goes to infinity, so then this is going to be equal to 0. And then you could account this as C naught plus delta W over lambda volume. Okay? Of course, solution can be additive. And of course, you have to represent W as a combination of particular solution between the initial and the final. Now let's go for the next one, linear. What's linear? Let's plot it here. If we have time, if you have loading first. Let's say initially everything was clean, and at time initial, the loading was linear. This is linear, and the slope of that linear line is 1, and the slope line is beta, and that is the slope of the line. And then if you want to plot this in the concentration way, time, concentration, and this is T naught. And initially the concentration would be the same as the loading. It will be linear. But the problem is that this is the concentrations because of the loading. The problem is that some system, if there is a linear loading, will get overwhelmed initially with the load. So it will not starting showing the concentration until later. And they call this as, I'll show it to you right now here, shock to the system, and the concentration will not be shown until later. So you will have, and realistically, we will have a lag. And this lag is equal 1 over lambda. And of course, this is here, the lag is here also, can be considered 1 over lambda. And the concentration will be showed like this, that because of the system is being overwhelmed by the load, and then goes straight line later on. So later on, the concentration would not be linear from time 0. It will have a lag, and then later on it will go linear. Since the load is linear, the concentration would be later on linear. And the slope of the line would be 1 over beta. And this called the late time slope. Okay, the late time slope. So how could you represent this? dc over dt plus lambda c equal beta t over volume. And if you solve it, ct is equal beta, which is the slope. You can see it here. This is the beta is the slope, beta over lambda volume. T, the time that you are taking the spill of the linear load, minus 1 over lambda, which is the lag time. T over 1 minus lambda, beta over lambda volume. This is the way of doing the ramp loading. Now let's go for the exponential loading. Exponential loading is a little bit weird. Okay, here we have to plot it like this. If you are plotting time versus loading, and initially at t0 there was a spill, so it will increase, and then later on the spill will have an exponential degradation or exponential removal of that spill, and this is an exponentially decreasing mass loading rate, and that's why we have to make it minus beta. Okay, let's say minus beta e, beta for exponential. So this is minus beta exponential. Sometimes you'll have an increasing load exponentially increases. It's not exponentially decreasing. So if it is exponentially increasing, so this is 0, and then at time 0, it will increase exponentially, and that's going to be plus beta e. So this is minus beta e, and this is plus beta e. Okay, so let's do it for the minus now. We're not going to be mixing between minus and plus. Let's plot the concentration for the minus BE or beta E. This is the concentration, and this is the time. You will eventually, at time 0, in the exponential loading, the concentration will increase from 0 to a maximum, and then goes down back to normal or 0. And this is the critical time. And this is the critical concentration. Okay? That point is very important in design. That is a very important design because we want to find out what is the time to reach critical point where everything is really high concentration. And that is for beta minus beta. So let's just do it like this. Wt is equal to 0 if t is less than t naught. W2 is equal to We to the, this E is here, sorry. We to the W loading E to the power minus beta 1t. So it's like this, W and then E minus beta 1, it's exponential, times t. If t is higher than, that's why you can see the minus, because it is decreasing. It is decreasing. If it's increasing, it's going to be a plus. So let's do the equation for that. dc over dt plus lambda c is equal W E minus beta 1t over volume. If you solve it, concentration at any time t, loading over volume, lambda, plus or minus, depending on, if it is plus, it's increasing. If it's a minus, it's decreasing. So depending on which one you're going to use, times E plus or minus, depending on, is it the exponentially increasing or decreasing? Okay, T minus E minus lambda T. Okay, so this is plus or minus depending if it's the exponential is increasing or decreasing, and this is plus or minus depending on the exponential is decreasing or increasing. Okay, now what is the critical time? So the critical time, it's where we have to mention now, it's the equation. Again, you could look at the book and you could see if you want to look at the derivation and if that's going to be important for you. For me, it's not important to look at the derivation of the differential. I'll give it to you right away. Remember, when you want to identify the critical time, concentration will go to a higher value, critical concentration, and will go back to a minimum value. This is T, and this is concentration, and that is TC, critical time, and that is CC, critical concentration. And that is only for exponential loading. So critical time, TC, is equal ln beta over lambda over beta minus lambda, and that is the critical time. If you want to find out the critical concentration, and that is the equation that's in chapter, that's equation 4.19. 4.21, the critical concentration, loading for the exponential loading over lambda volume, beta, which is the slope of the line over lambda, to the power beta E over lambda minus beta E. You could look at the book, and this is equation number 421 for the time critical and concentration critical, and that's completely up to you to look at it, to just understand, but you don't have to do it. You should know these equations. We'll try to do this exercise quickly, and that exercise it shows how to combine both multiple loads, and that's how to do the time of shifts. The goal here is to predict chloride concentration in Lake Michigan. Remember, chloride is conservative. Remember, the chloride, it will not have a K. There is no decay because there is no reaction. And also, there is no VS because chloride cannot settle. So no settling, no reaction, so K is equal to 0 and VS is equal to 0. And now, let's look at the example. We have the load. It's linear loading of road salt and exponential loading due to population. So let's look at loading. Initially, it was equal to 0. Again, you should go and look for this example if you want to look at it. But we will try to show initially it was 0. And from 1930, this is according to the example, until 1960, the load changed. 13.2 10 to the 9 T minus 1,930, and the whole thing is gram per year. And that is from 1930 to 1960. And that is, you can see it from the question, it's a linear loading. Let's look at the other loading, which is initially it was 0, and then later on it's 299 10 to the 9. And that is the loading. You can see here, this is the slope, e to the power 0.015 t minus 1,900. And that is beta A. You could see here, this is exponential. This is exponential loading. Okay? So we have the volume, and we have the outflow flow rate, and we have the background. So this is the background concentration before 1900, 3 milligram per liter. Let's look at, if we have space here, let's see. Okay, let's look at this. Let's try to draw it. Initially, pre-1900, beginning of the century, we have no information. We have background only, which is the 3 milligram per liter. C is 3 milligram per liter. And the loading, it's background. We could go back and check it numerically, but we're not interested of before 1900. Now, this is number 1. So if you plot it, it will be like this. This is time, 1900. And then 1930. And this is concentration. Initially, it was 3 milligram per liter. This is 3 milligram per liter. Okay. Let's look at the next the next interval. Number 2, from 1900 to 1930. You can see that you have the background first, because the background is the background. It's coming up from a previous loading, plus there is exponential. Okay, exponential loading, of course, W. And thus you could use the equation that we have. Remember the equation that for the exponential loading and the background, Ct is equal the background C naught plus loading exponential over volume lambda plus the slope of the beta of the line times E. And since this exponential loading is increasing loading, so E plus beta. And since we're starting to do it after 1900, it's T minus 1900. If you do it like, let's say, if you do it in 2000, so it's going to be 2000 minus 900. So that's going to be almost almost 2000. So 1900, so you're going to have almost 100 years, okay, as the time interval. Minus E, minus lambda, T minus 1900, and that's all of it can be considered the exponential loading. And this only can be considered the background loading. So now, let's plot it here. If you plot it, you can see that there is an exponential loading. If you assume that after 1930, there was a linear, and you can see the example, so you could assume it's going to be linear here. But that's not going to be actual, because now you're going to have linear, exponential, and background. Let's look at the next interval, which is 1930 plus. You could apply it to 2025. So in 1930, you have background, you have exponential, you have linear. So Ct, concentration T, C naught, background plus WE over volume over lambda okay, BE, and we're still doing the exponential loading. And now we're going to do the linear. Beta linear, lambda volume. Oh, I think it we'll have a hard time writing this here, but let me do it correctly. Lambda T minus 1930 minus, I'm going to write it here, minus 1 minus E minus lambda T minus, T minus 1930. And you close the parenthesis. And here we can see that we always, this is from year, this is before 1900, and this is from 1900 to 1930. That's why we put initial 1900. And here we put 1930 and later. So this is going to be considered for the linear, this is going to be exponential, and this is going to be the background. Okay, so what will happen now? It will happen now that the additional linear, it will force it, it's not going to be linear anymore. It's not going to be linear anymore. It's going to be exponential with the linear contribution. So that's going to be the initial concentration later on. Exponential and linear can be later on exponential at the end. And of course, that's not going to be considered like this. You have to find lambda. And again, lambda can be found easily. Let me just show it. Lambda can be found easily if you just do lambda. Q over volume plus K plus settling velocity over h. And since this is 0, this is 0. Q over volume, you know the Q is given 49.1 10 to the 9 meter cube per year. Let's see, 49.1 10 to the 9 meter cubic per year divided by the volume. Volume was given 4,880 10 to the 9 meter cube, and that would give you 0.01 per year. And then later on, you could find everything. And of course, beta was also can be found easily from the given loads, and everything else is well established. You could look at the book and find out how to do the final calculations. Most of the time, if you understand how to figure out exponential and linear, you can do it easily. Let's look at this very important example, because doing reaction in series is very important. And this is going to be the last exercise, I think.